Yeah, then good morning and welcome to Statistical Methods 2021. Happy New Year. And yeah, so the aim is now to discuss the GLM not only from a model formulation perspective anymore, but from a model estimation perspective. So that's the big topic for the next couple of weeks, to understand how the parameters are estimated and what the frequentist distributions of these parameter estimates are. But before we delve in, is there something that you would like to discuss that you feel cannot wait to discuss until 3 today? So something urgent that needs a resolution before we continue with our exploration of the GLM. Okay, apparently that's not the case. So then let's start properly. So the aim today is to discuss maximum likelihood estimation and parameter estimation in general in the GLM. And let's first briefly review where we went up to. So what we have been concerned with from day one is the general linear model, which we've seen we can write in this form. Stating that we assume that an n-dimensional data set, for example, the time series of a given voxel in an fMRI recording, because that's the application of the GLM in fMRI data analysis, is given by the product of a design matrix with some beta parameters. The design matrix, of course, comprising the values of independent variables. So, for example, the presence or absence of condition during the recording of an fMRI dataset at given time points, times beta parameters encoding the contributions of these independent variables to the observed data, plus normally distributed error terms, which can be summarized in this error vector epsilon, which is assumed to be distributed according to an n-dimensional multivariate normal distribution with expectation parameter 0 n, so n zeros stacked on top of each other, and covariance matrix parameter given by sigma square in, where the sigma square is a scalar larger than 0. And what we did before the Christmas break is that we basically looked at the various aspects of this model. So we first looked into matrix multiplication. Well, first we introduced what numbers are and stuff, and then we looked into matrix multiplication, and then we spent some time to introduce the notion of random variables and the notion of density functions, such as the multivariate Gaussian density function. And then we ended with essentially establishing, based on the transformation of random variables, establishing that this GLM is the same as essentially oops, I don't mean mu, is the same as stating or assuming that the data have a probability density function that is given by a multivariate Gaussian with expectation parameter x beta and covariance matrix parameter in. So this is basically, this one line is everything that we did so far in this course. Sorry, I wanted to write larger than 0. So the key point here is that we established a probabilistic model, that is a distribution over data, and this distribution is given or describes the distribution of n-dimensional data vectors y, and this distribution is a multivariate Gaussian with a specific expectation parameter that depends on a design matrix which is fixed and given, and effect size parameters beta, as well as a variance parameter. And this is essentially everything that we did so far, and this is what I in the very beginning called model formulation. So we've now formulated a model. What can we do with that? Well, we can look at it from a mathematical perspective, and for example compute things like the expectation of the data or the covariance of the data, which of course are trivial here because we have a Gaussian, and then the expectation is just x beta and the covariance matrix is just sigma square in. Or analytically study other aspects of the data. For example, what happens if we apply certain functions to the data, and look at these distributions. What we can also do is of course implement such a model on a computer. So for a given design matrix and given parameter values, we can use a random number generator to sample that data and look at how data samples from such a model look. And then if we look at real data, we might get an intuition of whether what we can sample from this model and what we actually observe looks kind of similar. We can do that. It's a good exercise. It's not proper statistics, but it's what people in computational neuroscience earn their living with, and it's something that one can definitely do. The next thing after model formulation, which we've now accomplished, although we haven't seen all variants, so what we looked at in some detail were, I think, sampling univariate Gaussians and simple linear regression. We will of course see more variants of the GLM as the course proceeds, meaning different forms of design matrix and beta values that then refer to things like multiple linear regression. Well, we've seen that in a way, but also things like ANOVA and ANCOVA. The next thing after model formulation is of course model estimation, or if you want, parameter estimation. And here the aim then is to get good estimates or good guesses for the parameters of our model, and the parameters of our model are the beta parameters and the variance parameters. So we want to figure out parameters. We want to figure out good guesses or point estimates for our parameters. And to do that, we need to assume two things. First, we need to assume that there are true but unknown parameter values in the world. So we assume that the data that we have observed were sampled from such a model, and the parameter values when the data were sampled were fixed to what is known as the true but unknown parameter values. So that's one assumption. So of course our model does not generate any data if we don't assume any values for the parameters. So we need to assume that there are these true but unknown parameter values, and our aim is now to estimate these true but unknown parameter values by point estimates. And point estimates are just guesses of the parameter values, and we will denote them with a hat. So for example, if our beta is corresponds to or if our whole GLM corresponds to a simple linear regression model, then of course we have an offset and a slope parameter in our beta here. So we assume that there is a true but unknown offset parameter, a true but unknown slope parameter, and they have certain values, for example 0 and 1. And based on the data that we observe, we're now trying to come up with a good guess for these true but unknown parameter values, and these are then our estimated slope and offset parameters and variance parameter in the context of a simple linear regression example, but more general, our beta parameter estimates. And if you've seen any fMRI data analysis, beta parameter estimates are what you're always looking for, not slope and offset parameters, because fMRI data analysis in the GLM context rests on multiple linear regression and not on simple linear regression usually. So that's what we want to do, and to do that, or while doing that, I take the possibility to, or I use this possibility to introduce you to a more general means to estimate parameters in probabilistic models, and this is known as maximum likelihood estimation. So what we actually want to establish today are the maximum likelihood estimators of the true but unknown parameters beta and sigma square. Oops. And once we have estimated these parameters, we can of course do something with them. For example, looking at the distribution of these parameter estimators, or looking at the distribution of function of these parameter estimators, such as t statistics or f statistics. But first we need to actually figure out estimators for these parameters. And yeah, we will be guided by this idea of maximum likelihood estimation, and yeah, that's actually what we want to do. Questions so far?
I'm not sure if I understood correctly, but did you say that there are two assumptions? And the first one is that there are parameter values that are true but unknown, and they exist.
Mm-hmm.
And is the second assumption the aim?
No. I don't know. The assumption is, the core assumption is that our data have been generated from such a model. And then, of course, the assumptions are that this is a sensible model, and of course this model only generates data if you assume certain values for the parameters. So that's, I think, what I said. No, and our aim is, of course, to estimate the true but unknown parameter values, because they encode how much, for example, our independent variables contribute to the data. So these are then, if you look at simple linear regression, these are the values of your slope and offset parameters that you would like to be estimated, or in terms of ANOVA that we will see later, these are effect sizes of your different groups and so on. Yeah?
Yeah, thank you.
Good. So the principal method that we are trying to look here at is maximum likelihood estimation. Which we then want to apply to the GLM in the second hour. And I still cannot scroll, although it's 2021. So the fundamental idea about of maximum likelihood estimation is the following intuition. Use those parameter values as point estimates for which the probability of observing, or the probability of the observed data is maximal. Now, so the idea is I have some data, and I assume that these data were generated under a probabilistic model with certain true but unknown parameters. The question is, what are the what are good guesses for the true but unknown parameters? That's a little bit too small. And the fundamental idea is then to use those parameter values under which the data that I have actually observed has the highest probability of occurring. That and the fact that maximum likelihood estimators actually have a certain nice qualitative features that we study in statistics for data science are the motivations for looking into maximum likelihood estimators in the first place. Now, if we want to do maximum likelihood estimation, we need to, of course, define what things are. And the first basic concept that is required for maximum likelihood estimation is the notion of a likelihood function. And a maximum likelihood estimator is then a value of a parameter that maximizes a likelihood function. So what's a likelihood function? A likelihood function can be written as follows, and this then also allows to explain what it is. So a likelihood function is a function. So remember that we discussed functions. And as its domain, takes the parameter space of a probabilistic model and returns a scalar number, so a real number, which actually is usually, because it refers to a probability larger or equal to 0, and so it allocates to each value in parameter space a value of the log likelihood function, and this value it assigns to it is the probability density of some data under a given model. So let's link this with what we've seen here. So what we established for the GLM is that our data has this probability density function. Now, a likelihood function considers the probability density of the data as a function of the parameter, and the parameter, of course, here in the case of the GLM comprises both the beta parameters and the variance parameters, and such that our parameter space here is given by the p-dimensional real space. So remember, the beta parameters are p-dimensional vectors. So for example, for simple linear regression, 2-dimensional vectors, slope and offset parameter. And the variance parameter is always positive, because otherwise the Gaussian is not defined. And hence our parameter space is given by the Cartesian product of the p-dimensional real number, the p-dimensional real number space, or space of p-dimensional real vectors, and the positive real values, real numbers. Now, the crucial difference here is, and this is always confusing when one first is exposed to maximum likelihood estimation, is that this here and this here is of course the same thing. The crucial difference is that a probability density function is a function of these values y here, so it assigns to each value of the data, it assigns a probability density according to this expression. A likelihood function, on the other hand, assigns to each value of the parameter this value for a fixed value of the data. Yeah. So to make this maybe even more prominent here, we could again express the functional form here of our density. So this is a function from the n-dimensional real numbers to the positive real numbers, and it allocates to each y the value p theta y, p beta y according to this definition below. Let's zoom a little bit in, then we have so. Go a little bit closer here. So that's on the left side we have the likelihood function. On the right side we have the probability density function. And probability density functions we have of course studied previously, so they integrate to one and stuff, but likelihood function we haven't seen before. The confusing thing, or the crucial thing here, is that the value that is assigned to or that corresponds to the value of the likelihood function, and this corresponds to the probability density function, is the same. It's the probability density, usually in our case, of data based on some parameters, but the functional dependence is different. So this is a function of the parameters for fixed data, and this is a function of data for fixed parameters. Yeah? Now, the idea of maximum likelihood estimation is then to, as I said here, or already wrote down, is to use those parameter values as point estimates for which the probability of observing the data of interest is largest. So we are dealing with a function optimization problem like we discussed in calculus to some degree. Namely, we want to find that value of theta and we call this the maximum likelihood estimate, which maximizes the likelihood function. Yeah, so we you can get this a little bit nicer by doing this. So we change our parameter value theta for fixed data, and change the parameter value such that we maximize the likelihood function. Maximum likelihood estimator. So in this scenario here we observe some data y, and now we change our beta values and our sigma square values such that this value p beta sigma square y becomes maximal. The data we cannot change, the data is what we observed, but we can change our guess for the parameters. And in fact, if you're using numerical maximum likelihood estimation, this is really what you do. So you change the parameters, look at the value of the likelihood function, and if it has increase, you're happy, and use maybe these values of the parameters, or you then change them a little bit more and see whether the likelihood function increases further. In the theory of the GLM and in most kind of tractable statistical models, one can do maximum likelihood estimation analytically, meaning like you can analytically determine where the maximum, or let's say the minimum of the function x square is, like we did in calculus. You compute the first derivative, you set to 0 and you solve for the minimum. You can use the same analytical maximization approach for simple probabilistic models such as the GLM, and this is what we will look at. So we will try to determine the maximum likelihood estimator of the GLM by using an analytical approach, which then rests on computing derivatives and setting to 0 and solving. Commonly, so actually we should write this down. So candidate values, of course, for the maximum likelihood estimator fulfill this criterion. This means at the location of the maximum likelihood estimator. Oops. What is this? Here. Well, at the location of the maximum likelihood estimator, equals 0, and this 0 can actually be a vector if this whole theta is a vector, and this, what I just wrote down here, that the derivative of the likelihood function is 0, this is also known as a likelihood equation, because it's a system of equations that if you solve it for theta gives you a maximum likelihood estimator. Now, one last thing before we can address some question is that commonly, instead of maximizing the likelihood, what is being done is that we work with the log likelihood, which I denote by L, and which just corresponds to the log of the likelihood. The log of positive numbers actually for 0 is not defined, and for positive numbers takes on negative and positive numbers, so we just have the real numbers here, and it assigns to each value in parameter space the log of the likelihood function, which is of course then, given the definition of the likelihood function, the log of this probability density. And because the logarithm is a monotonically increasing function, the location where the likelihood function has a maximum, hence a maximum likelihood estimator, is also a maximum of the log likelihood function. Yeah, so the because it's monotonically increasing, if the value of the likelihood function is larger for, let's say, theta 1, then the value of the log likelihood function is also larger for theta 1 compared to some other theta value 2. The benefits of the log likelihood functions are things like that products that are often occurring in likelihood functions, because one uses the joint density of data, get turned into sums, or, and this is what we will see, because we have this independence property already built in our multivariate model here by means of the covariance matrix parameter, but we have an exponential expression here in the multivariate Gaussian. Exponential expressions go away, so the log likelihood function makes the mathematical treatment simpler. So that's one of the main motivations, actually, to look at log likelihood functions. But then again, the same approach here is to look at the derivative, set to 0, and solve by looking at the log likelihood function. So for and these are then called, if you want to be formal, log likelihood equations. And as you can see, we have in a way already some access to the log likelihood, sorry, to the likelihood function of our model, because we have an expression for that. But these things, we haven't really formally written down the likelihood function, and we also haven't derived these maximum likelihood estimators yet. So this is what we want to do. But before we do that, are there questions regarding this? Or maybe let me finish with one thing to establish really the to bring that home again. So one can then summarize maximum likelihood estimation as the following procedure. It's a three-step procedure. First, formulation of the log likelihood function. So if we want to find some parameters that maximize the likelihood, then of course we first need to write down the function that we're actually trying to maximize. Then we want to find a maximum, and we do this via the necessary condition for a maximum. So we evaluate the log likelihood function derivative / gradient if we are dealing with a multivariate log likelihood function, which we will actually do when we look at the GLM, and then we solve a solution of the log likelihood equations for the parameter of interest. So we need to solve this equation here, the log likelihood equation, for parameter of interest. So that's maximum likelihood in a nutshell. Again, the intuition, make this bigger here. The intuition is to choose that parameter value to choose that parameter value for which the data have the highest probability of occurring. And I still don't get it bigger. And formally, it's then this three-step procedure of writing down the log likelihood function, computing its gradient, and solving the log likelihood equation. Yeah, questions about this general procedure? We will do this in detail for the GLM in the second hour, but first, are there questions regarding this idea? Apparently not that many. One thing that is, of course, always of interest if you do analytical function maximization. Yeah.
So my question is like, so in model formulation, like, so the means like it belongs to the Gaussian distribution, right? Based on the error, because error belongs to the Gaussian distribution. Is it right?
Yeah. So in the GLM, yes. So we're talking about the GLM right now, right?
Okay. Yes. Thank you.
Yeah. So one thing that's always of note is that if you write down these log likelihood equations, you're looking, of course, only at the necessary condition for maximum, and in principle, you would also want to look at the sufficient condition, meaning that you look whether the second derivative is negative. most of the functions that one is dealing with, and this is something that I also then write in the script about, is that you're dealing with concave log likelihood function which have unique maximum. So if you find some point in parameter space that fulfills the necessary condition, it also definitely will fulfill the help. I have some noise here. It will also fulfill the sufficient condition. And then what you also find in the script is a discussion of a maximum likelihood estimation for univariate Gaussian. So as a first example of getting into that, of course, the univariate Gaussian distribution and sampling from a univariate Gaussian distribution corresponds to a specific type of GLM. So one can, of course, also derive the maximum likelihood estimators for the univariate Gaussian based on looking at the maximum likelihood estimators for the GLM, and then looking at the special GLM case that corresponds to IID sampling from a univariate Gaussian. So this is something that is in the script that we will now not discuss, but which gives you a first idea of how things work. Good. So if there are no questions regarding this general procedure, then I suggest we take a break now, and after the break look into the application of this general framework that I've just now here sketched to the GLM, so that we end up with estimators for our true but unknown beta and variance parameters. Okay, now any questions? Doesn't seem to be the case, so then let's continue at 10:30. Okay, then let's continue and now have a look at how we can apply the maximum likelihood procedure to our probabilistic model of interest, namely the GLM. And we will do that in a stepwise manner. So we will first assume that we are not concerned with the estimation of the variance parameter and are only concerned with the beta parameters. And once we have found a maximum likelihood estimator for that, then we will deal with the variance parameter. Yeah, and essentially it's about applying this procedure here: formulation of the log likelihood function, evaluation of the log likelihood function derivative or gradient, and then solution of the log likelihood functions. So let's maybe put that here: beta parameter, maximum likelihood estimation. So the first thing that we need to write down is the log likelihood function, and of course this is the log of the likelihood function, so it pays to first write down the likelihood function, and we already have everything that we need for that. So we now consider only the estimation of the beta parameter and take for the moment sigma square as fixed and given. So our parameter space for the beta estimator is of course the p-dimensional real number or real vector space, because we have p beta parameters which take values in the real numbers. We have a Gaussian which is always positive, and Gaussian density which is always positive. We allocate to our betas the value of the likelihood function, and the value that we allocate is already written to the left here. It's the density of some data y, so a data vector y, under or given these parameter values, and for this we have a precise definition, namely a multivariate Gaussian density over Y with expectation parameter x beta and covariance parameter sigma square n. And of course we can write out this, so maybe we put it down here because it's always the same. We can write out this. We of course studied the functional form of the multivariate Gaussian, and if we write it out in full functional form, then what we get is 2 pi sigma square to the power of n half minus to the power of minus n half. And this is a square here, which if you go back to the general formulation of the multivariate Gaussian relates to the fact that we here have the determinant of the covariance matrix parameters of this the inverse of the determinant of this matrix here, and because this is a diagonal matrix, all the diagonal elements which are sigma square multiply, and then we get to the power of n, and we take the square root power of n half inverse, so the minus, and we have this 2 pi to the power of minus n half anyway. So this is where this term comes from, and then we have in the exponential we have this, which is essentially just how any multivariate Gaussian looks, with the fact that the inverse of the covariance matrix parameter sigma square here is 1 over sigma square in, and in doesn't do anything, so it's not showing up between these two terms in here. So that's then our likelihood function, and again this is just the multivariate Gaussian probability density function with expectation parameter x beta and covariance matrix parameter sigma square in. So it's actually, if you are happy with the multivariate Gaussian density, there's nothing new in here. Now the first new thing then is to actually write down the log likelihood function, which as explained on the left is of course just the log of the likelihood function. So we now get all sorts of values, and here are concerned with the log of the probability density of the data under the model, which is of course just the log of this. This is actually an equality here, that's not a definition. And hence we are evaluating the log of this expression here. This and this. And then the log, as we learned in the essential functions part, of course has what's this? Sorry. The log has of course many nice properties. Once I manage to write it down nicely. That's what I wanted, because it turns products into sums, and it removes the exponential, so we get a simpler function here, and it turns powers into products. So what we actually get is minus n half log 2 pi minus n half log sigma square, and the exponential, the log is the inverse function of the exponential. Someone wants to... Why does it select this when I'm pointing here? Anyway, so we get minus 2 sigma square y minus x beta y minus x beta. So that's then our log likelihood function. Again, we consider it here as a function of beta. The y is fixed, and sigma square we for the moment assume known. Now what can be shown, and this is what I will show you based on the script then, is that the log likelihood equation here, so doing this, so essentially the derivative of the log likelihood function with respect to the parameter vector beta at the location of the log likelihood parameter of the maximum likelihood estimator being 0 corresponds to the following system of equations. Which are known as the normal equations. There you already see the proof. So what I'm saying here is that if you compute the derivative of the log likelihood function, so evaluation of the log likelihood function derivative, which is here a gradient because you have a vector, you have a multivariate log likelihood function, and set it to 0, then you get a system of equation which corresponds to this system of equations that are put down here, namely the transpose of the design matrix times x times beta equals the transpose of the design matrix times y. Why this holds, I have down here, and I will explain in a second. But right now I'm telling you that this is equivalent. So computing the derivative of the log likelihood function and setting to 0 corresponds to, and setting to 0 is implies this set of equations. What is a little bit complicated here, or complex, is that we compute the derivative with respect to a vector, and this leads into matrix differential calculus, and this is all a little bit there are different ways to address this. So one way to address this, and is the way that I do it in the proof. In any case, we have this equivalence relationship that the setting the derivative of the log likelihood functions, log likelihood function for beta to 0 is the same as this set of equations here, the so-called normal equations. And these normal equations we can now straightforwardly solve if we can invert xt beta. So if we want to solve the normal equations for beta, then we can call this our maximum likelihood estimator. then we can of course multiply both sides with the inverse of xt x. So if on both sides we pre-multiply from the left with this, then of course we get the solution, namely that that beta ml, oops, there's something missing, that the maximum likelihood estimator here is given by the transpose of the design matrix times itself, and the inverse of that times the transpose of the design matrix times y. This works as long as we can find, as long as xt times x actually has an inverse, as long as this is invertible. And like I write in the script, in linear algebra, one can show that if the design matrix is of full column rank, then, so if there are essentially, if the design matrix columns are not completely collinear, then one can invert this product here, so this xtx, and then one can solve this. Depending on the collinearity of the design matrix columns, this works more or less. So this is why it always makes sense to think a little bit about the design and not, for example, in fMRI present different conditions exactly at the same time all the time. But in general, we can assume that our design matrix is of full column rank, and then we get this solution for the maximum likelihood estimator for the beta parameter. And we will look a little bit more into an understanding of these formulas when we look at examples. If we look at, for example, one simple t-tests or IID sampling, then of course for specific design matrices, this expression takes on a specific form. So without showing that now, for example, if you take just a column of ones as the design matrix, then what actually comes out is just the average of the data points. So you estimate the expectation parameter of n univariate Gaussian random variables by the average of the data points. We will look at these examples later on, but in general, it takes this general form. What I haven't shown you yet is that actually computing the derivative or the gradient of the log likelihood function implies these normal equations, so I will have to do that now. But first, are there questions in a way regarding that we now have a solution for the beta parameter maximum likelihood estimator? Okay, apparently not. So the magic or the magic trick that was used here was to say computing the gradient, so the partial derivatives with respect to all beta parameters corresponds to this, and setting to 0 corresponds to this set of equations. And this is what you find in the script as proof of 832. It's currently in my version, and there I can explain a little bit more now, but I don't want to type this because then I would just introduce many typos. So let's maybe do that here. So the question is, why do I say this thing here? So that's the question. Oops. So this follows as follows. If one doesn't want to use matrix differential calculus, then one can see this as follows. So first of all, we need to realize that we have a log likelihood function that is a function of a vector. So we have a multivariate real-valued function, and of course the first derivative of this is a gradient. We set the gradient to 0, and the gradient is of course a vector with as many entries as there are parameters. So our here somewhat intuitively written down d beta ly equals 0 actually corresponds to the gradient of the log likelihood function at the location beta being equal to the 0 p-dimensional vector. Of course, the entries of the gradient are the partial derivatives of the log likelihood function with respect to each parameter. So this, of course, implies that the partial derivative of the log likelihood function with respect to each beta j is 0, where I already realize a typo because it should say equals 0. So there. So what this? Maybe I should have typed it out. After all, it should say partial. So the partial derivative of ly with respect to beta j equals 0 for all j1 to p. I will put that into the script. Now the partial derivative is of course of our log likelihood function. Our log likelihood function we have up here. And we are interested now in the partial derivatives with respect to the beta j. And of course here we don't have any beta j's, here we don't have any beta j's, so these terms evaluate to 0, but then we need to compute the the partial derivative with respect to beta j of this term here, and this is what I then write down here. Given the functional form of ly, the above is equivalent to the partial derivative of this latter term being 0. So this being 0 is missing there. Now here the only thing that can be 0 is actually this latter term here, because sigma square cannot be 0, so we can ignore that, and then this expression is 0 if this expression here, so the partial derivative with respect to beta j of this product yx beta t times yx beta z is 0 for all j to p. And the 1/2 we could remove as well, but we keep it because we will have we have squares in there, and then the 1/2 gets rid of a 2. Now if we do that, we actually have to start calculating a little bit. So what we do then here is to first write down this vector dot product in terms of its sum. Here the yi and x beta I are the ith entry of these vectors. Remember that y is a vector and x beta is also a vector. And then it's just differentiation, so using the chain rule, so the derivative of the outer function, which then gets rid of the 2, the derivative of the inner function, then maybe is there a sign mistake, maybe not. The y definitely goes away, and then we are left with computing the partial derivative of the ith row of the expectation parameter of the Gaussian, which is given, and this is maybe something you remember from the very first session, by xi1 beta 1, xij beta j to xip beta p. If we compute this partial derivative, of course there's only one beta j that corresponds to xij. Here we can also write that out, and then we can multiply everything in. And then we end up with these sums, xij, yi, so that's from multiplying in, xij, xi1, beta j, and so on, up to xij, xip. And this set to 0, we can then move this first term here to the other side. And this, of course, can be done for all j's, or has to be done for all j's, which we can then write one below the other. So the first j in the first line being equal to this, second, and so on. And then we can rewrite this expression here as a matrix product of these sum terms times our beta parameters, and we can rewrite these remaining sums here as the product of the transpose design matrix with itself, which then yields on the left side here this xt x beta. And we can rewrite this expression here as the product of the transpose design matrix with the vector. So the principal idea of this proof is we look at the partial derivatives of this expression here, get very many sum terms with very many indices, and then realize that we can rewrite these sum terms with the very many indices again in terms of matrices. And then we see that actually these very many sum terms that result from the partial derivatives correspond to the matrix product xt x beta and xty. So this is where these are the details of where this thing is coming from. Now again, like we already saw, once this thing, the normal equations are established, then to find the maximum likelihood estimator for beta is fairly trivial. We just need to invert, or be able to invert xt times x, and then we get, as the solution for the maximum likelihood estimator, get this expression here. Okay, so that's essentially what I want to say with respect to the derivation of the maximum likelihood estimator for the beta parameters. Are there questions about this? Apparently not. So we will use this estimator now all the time. We know that it's the maximum likelihood estimator. There are different ways to derive this, namely there's also an ordinary least squares approach to deriving this, which is something that I can tell you about in a second once I find again how I put this yellow. It's already yellow, but for this. So I will not constantly refer to this estimator as the maximum likelihood estimator, but just as the beta estimator. We know that this form is the maximum likelihood estimator, but because for the variance parameter we will actually not use the maximum likelihood estimator, I will just refer to this form here as the beta parameter estimator all the time now. Yeah. So this equation here, this one, that's crucial. So this is how, and have a look again what this says. If you want a good estimate for the beta, true but unknown beta parameters, you need to take your data into account and pre-multiply it by this expression that only involves the design matrix. Yeah? Design matrix you have by your design, data you obtain, and then you can compute your beta parameter estimate by pre-multiplying your data by the transpose of the design matrix times itself, the inverse of that times the transpose of the design matrix. Yeah, one thing we can maybe without writing it down, you find a description of that in the script, establish is that what we try to do here is maximize this term here, or this function here, which involves this minus term minus 1 to sigma square y minus x beta t y minus x beta. Of course, the same thing as maximizing this negative term here is to minimize the positive term here. And the positive term here is of course the difference between the observed data and the predicted data based on the value of beta. And this of course shows up in a square form here, as you see, for example, down here. So ordinary least squares estimation, which only tries to minimize the squared deviations between data points and predicted data points, you can either view as a special case of maximum likelihood estimation, or you maybe view it as completely something that just doesn't invoke the Gaussian form. So instead of using this probability density, you focus on this term here, and instead of maximizing the negative form, you minimize the sum of error squares, which is just this form. But this is completely equivalent to doing maximum likelihood estimation. So the maximum likelihood estimator and the ordinary least squares estimator for beta in the GLM are identical. And the reason that I introduced the maximum likelihood estimator and do this whole thing based on the Gaussian assumption from the outset is that we will use t-values. And t-values only show up if you have Gaussian error assumptions in there from the beginning. In ordinary least squares, there's no reason why at one point you should have a t-distribution if you didn't assume Gaussian errors from the beginning. So essentially the result here is the same for ordinary least squares estimation. The assumption in ordinary least squares estimations are fewer, but then they also have fewer consequences in the sense that you have no analytical distributions for your parameter estimates and statistics that result from this setup. Now the final thing for today then is to derive the parameter estimator, the maximum likelihood parameter estimator for the variance parameter. So we now consider that. Any remaining questions regarding beta parameter estimation?
Excuse me. So actually, in beta parameter, like if we calculate it, like, so sometimes it might possible like x may not have the full rank. So then how we will calculate the inverse, because it may be possible.
No, then you cannot, then it's not estimable, but there's a more advanced theory about the GLM that shows that even if you can't estimate the beta parameter vector, there are still contrasts of beta parameter vectors that you can estimate. So yeah, essentially you will need to open the pages in the statistics books then that deal with non-full rank design matrices. So we don't cover that here.
Okay, thank you.
Good. So then let's go finally to variance parameter estimation, and maybe we do that here. So the variance parameter maximum likelihood estimate. Yeah. Maybe let's not do it like this. Now I destroyed everything. What just happened? Or we do it down here. There's this space. Somehow this whole thing with the one node doesn't really help me. So now we're interested in variance parameter maximum likelihood estimation. And here we again are interested in writing down a likelihood function. Now this is of course not a function of a p-dimensional vector because it's not a function of beta, but it's a function of a positive number. And it allocates to sigma square the value of the likelihood function, which is of course still the same. Yeah, so we are still dealing with a multivariate Gaussian, so actually nothing changes here, so we are still interested in this, which also means we can directly use our log likelihood function by just adapting the functional definition, but it's the same thing, just that we're looking at it as a function of sigma square now. So we still have this. And then we are of course still required to evaluate the derivative of the log likelihood function, which in this case then is a little bit more straightforward, because we are just have a scalar, we have a univariate real valued function, so we just compute the standard derivative with respect to a scalar and not with respect to a vector. So if we then want to do this, for our maximum likelihood estimator here, then we just need to evaluate the standard derivative of our log likelihood function here. Which is of course just the derivative with respect to sigma square of our log likelihood function. And this then evaluates as follows. So this, of course, this corresponds to, with the linearity of derivatives, corresponds to the derivative of the first term here, this minus n ln 2 pi. There is no sigma square in that, so that, maybe let's just write down the solution. So this goes to 0, minus n half remains. And the derivative of the logarithm of sigma square is 1 over sigma square. Jesus. And here we have sigma squared to the power of -1, and if we compute the derivative of this, we need to subtract 1 in the exponent, so we get to the power of -2. Sigma squared to the power of 2 is sigma 4, and the minus sign gets removed because we have -1, so we get 1/2, because the constant stays, sigma 2 square, which is then sigma 4, and the coefficient here remains. So, and now we see that our derivative still depends on beta hat, on beta. And if we now set to 0, we will get a solution for our estimate for sigma square, but it will depend on beta, and we don't know the true but unknown beta value. So the solution for that is then to replace the true but unknown beta parameter value in the log likelihood equation by the estimate of beta. So our log likelihood equation looks as follows. This here, but we replace this by our beta hat. And set the whole thing to 0. Yeah. So that's our log likelihood equation, which we now want to solve for our estimate. And the first thing that we can do is, of course, multiply everything by 2, so that we get on the left side minus n, 2 goes away, and this. And happy with everything? I hope so. Yeah, and then we well, maybe take this to the other side. What do I do it here? I have this there. Ah, yeah, so take this to the other side. Sorry. And then it's of course plus. I don't know whether it's better if I write it by hand, then nobody can read it, or I use OneNote, then I constantly write down crap. Yeah, finally isolate the variance parameter. So what is going on? Where's this now coming from? So put the sigma 4 on the other side, so that we here have sigma 4, which we then can, of course, reevaluate. So this leaves 1 sigma square, and then we can divide by n, so then we end up with our estimate being 1 over n, this expression here, which also has a name, namely residual sum of squares, and that's different from the error sum of squares, because the error sum of squares are based on the true but unknown parameters, and this is here based on our estimator for beta hat. So that's our maximum likelihood estimate for the variance parameter. So essentially you look at the squared remaining difference between the data and the data prediction based on the beta hat estimate, and that's all fine. That's the maximum likelihood estimate, but unfortunately it's not the estimate that is commonly used for variance estimation in GLM theory, because it's not the most awesome parameter ever. It's actually biased, so its expectation does not correspond to the true but unknown variance parameter. But this bias can be removed by dividing not by n but dividing by n minus p, which is the number of parameters, which you might remember if you're looking at estimating the variance of a univariate Gaussian by means of the sample variance. There you always divide by n minus 1, because you have one beta parameter, and this is the generalized version here. Different way to motivate this form that we're looking here is so-called restricted maximum or residual maximum likelihood estimation, that gives rise to this n minus p, but that's beyond the scope of the current course. So in summary, the maximum likelihood estimator for the variance parameter is given by dividing the residual sum of squares. So let's define that here. The residual sum of squares, that's just this term here. Dividing that by the number of data points minus the number of by the number of data points for the maximum likelihood estimator, and for the variance parameter estimator, for the unbiased variance parameter estimator, dividing by the number of data points minus the number of parameters. So that's the residual sum of squares, and somehow doesn't want to put me here. So in summary, what we have gained then today is that I've shown you how to estimate the parameters of this model. And let me go back to the beginning here. The maximum likelihood estimation I've shown you. What we will use as estimates here is actually the beta parameter maximum likelihood estimator or estimators, and the restricted maximum likelihood variance parameter estimator, and they have the following form. Hat beta is given by x t x to the power minus 1 x t y, and our variance estimator is given by the residual sum of squares, so y minus x hat beta oh Jesus divided by n minus p. So these are our estimators of interest. So model estimation in the GLM for all forms of GLMs that you can think of. So t-test, simple linear regression, multiple linear regression, ANOVA, ANCOVA, everything, the parameters are beta parameters and a variance parameter, and the beta parameters can always be estimated like this, if x is of course of full column rank, and the variance parameter can always and is always estimated like this. Yeah. And that's what I wanted to do today. Next time we will then look at the distribution of these estimators and statistics that derive from these estimators, namely, or next week, the t-statistic, which is a function of both the beta parameter and the variance parameter estimator. And in the script, at this point you find already the examples of univariate Gaussian samples and simple linear regression, which will, if you look at the simple linear regression, maybe relate back to things that you learned in undergrad psychology statistics, because they love that. So there you can see how the formulas that you learned for the offset and slope parameters in the simple linear regression design, how they fall out of the GLM framework if you use these parameter estimates. We will have a look at that when we talk about t-tests and simple linear regression. Then we will look at the specific forms of the beta parameter and variance parameter estimates for different designs, and hence also for simple linear regression. Good. Any questions right now? Okay, apparently not. Then we stop here. Next time talk about the distribution of these estimators, and yeah, meet again with the SCAN people at 3 o'clock for neurocognitive methods and programming. Bye bye.